Hello, this is Stat134, Lecture 15. You have an in-class midterm next Friday. There'll be a review sheet coming out today, as well as in-class review next Wednesday, possibly second half of Monday, and you'll be reviewing in section. So last time we were in section 3.6, talking about the variance of a sum of dependent indicators, and remember that came down to finding two probabilities, one P1, which is just the expectation of the expectation of the first indicator, for example, and E12 is the expectation of the product of the first two indicators. So then the expectation of x is n times P1, and the variance of x is n times P1 plus n times n minus 1 P12 minus NP1 quantity squared. Today we're going to go over the hypergeometric, the geometric, and the negative binomial. So hypergeometric is an example of a random variable which is a sum of dependent indicators. So for example, if x is the number of aces in 5 cards drawn without replacement from a deck of 52, then capital N is 52. There are G equals 4 good elements, and small n is 5 in this case. So here I1 is 1 if the first trial is good, and 0 otherwise, and that has probability big G over big N. And so the expectation of x is little n g times g over n. And the expectation, the indicator 1, 2 has probability g over n times g minus 1 over n minus 1. And hence the variance of x is what it should be. And you can follow through the algebra, which I provide you in the appendix here. And so I provide you with all the little algebra details, and this gives you an expression for the variance. So that's not super interesting. What's a little bit more interesting is really understanding what this expression is saying, and comparing it with the binomial. So remember that binomial has variance NPQ. So here we have NP and Q as well, but now we have this correction factor, which is a number less than 1. And so the variance for the hypergeometric is less than the variance of the binomial. And this arises because each success or failure that occurs reduces the probability of subsequent successes or failures. So you get values of x that are close to the mean. So if here's the distribution of the hypergeometric with its variance, in general you're going to get values for values of x that are close to the mean. When capital N goes to infinity, in that case, the hypergeometric becomes binomial. And when I say that the population size goes to infinity, I also imply that capital G goes to infinity as well. So capital G is some fixed proportion of your population that are good. So now we go on to section 3.4, which is the geometric distribution. So we've seen this before. X is the number of P trials before your first success. So it takes values 1, 2, 3, and so on. And the probability that X is K is Q K minus 1 times P. You have a P coin, and x is the number of coin tosses until the first heads, for example, and you want to find the probability that x is greater than k. So then you can just use the definition. So here, x being greater than k means that x takes values k plus 1, k plus 2, and so on. So you can just write out what all of these terms are, and you'll get a geometric sum. and just do a little bit of algebra, and you get that the probability that x is greater than k is q to the power k, a good fact to remember. There are some identities that are actually also important. So one is just our geometric sum identity. Now if we take the derivative of both sides of this with respect to q, we get the identity that the sum of kq to the k minus 1 is 1 over q squared. And if we take the derivative again, then we get the sum k times k minus 1, q to the k minus 2 is equal to 2 over p cubed. I bet you didn't know that, but now you do, and that will be useful to us later. So we're going to find now the expectation of x and the variance of x. So the best way to find the expectation of x is using the tail sum formula, which we covered in lecture 11. And because we know probabilities where x is greater than k in this case. So we can write the expectation using the tail sum formula, and we get a sum of these q to the power k, and that turns out to, just using the formula for geometric sum, to be 1 over p. So the expectation of geometric is 1 over p. Now the variance of geometric is q over p squared, and the derivation of this is not particularly pleasant, so I'm just going to go over it in an appendix here. So for geometric, we want to use a formula for the variance of x that involves the expectation of x squared minus x, because that is something we can calculate. So you can just follow my algebra here. The variance of x is the expectation of x squared minus x plus the expectation of x minus expectation of x quantity squared. So it just comes down to figuring out what the expectation of x squared minus x is. And for that, we can just use the definition. And our, so we use this definition and recognize then that we have that identity that we were speaking of earlier, that the sum from 0 to infinity of k minus 1, q to the k minus 2 is just 2 over p cubed. So with that fact, we can then find the variance of x is q over p squared. Just want you to have in your notes this derivation. So next, I want to warn you guys about that some people define the geometric distribution to be the number of failures until the first success, not the number of trials until the first success. So for example, if the number of trials to the first success is 5, that means you have q, 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 p. So then the number of failures to the first success would be 4, q, 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 right? So y is related to x as y is x minus 1. So then the expectation of y is the expectation of x minus 1, or q over p. The variance of y is the same as the variance of x. Finally, we did the negative binomial distribution with parameters r and p. The negative binomial distribution is a sum of r independent geometric distributions, and it's a generalization of geometric where r is just 1. So, for example, if r is 3, we would have a sum of 3 independent geometrics. So our first geometric is W1 here, which is, in this case, 4. It takes 4 trials to get the first success. Then after that, we have W2, which is 3. It takes 3 trials to get the second success. and then W3 just takes one trial. So let's call T sub R to be negative binomial RP. This takes values R plus 1, and so on. And TR is the number of P trials until the rth success, and it's also defined as the sum of R, IID geometric P. So the expectation of TR then is R times the expectation of W1. W1, we know the expectation of geometric is just 1 over P, so we get R times 1 over P. And the variance, we have independence as well, so the variance is just R times the variance of W1, so R times Q over P squared. So finally, we can write down what the distribution formula is. So the probability that TR is K, so that means that now the last slot has to be a P, that would be the R success. So before that, I have K minus 1 slots with R minus 1 successes in it. So the chance of that is K minus 1, choose R minus 1, P to the R minus 1, Q to the K minus 1 minus R minus 1, which is just K minus R. So then now don't forget, that you also have a success in the rth spot. So we have to multiply this by P. Finally, we concluded with the coupon collectors problem, which is a variation of geometric and negative binomial. So you have a collection of boxes, each containing a coupon. There are n different coupons. Each box is equally likely to contain any coupon independent of the other boxes. X is the number of boxes needed to get all n different coupons. So we want to find the expectation and variance of this. So let's just look at this as an example, where n is 3. So I have 3 different colored coupons, and X1 is a geometric till I get my first coupon, which is just 1. And then X2 is geometric till I get my second coupon. And that geometric has a different probability, but we'll talk about that in a second. And the third geometric X3 is for time till I get my last coupon. So then X is the sum of these, and each of these have different probabilities. So the chance to get my first coupon, I can have any 3 out of the 3 coupons, so it's geometric 1. X2 now, once I have 1 coupon, there's 2 coupons left that I can choose out of 3. So it's geometric 2/3, and finally X3 is geometric 1/3. And so the hardest part of all of this is just keeping track of the algebra here. So we have 3 different P's, P1, P2, and P3 with corresponding Q1, Q2, Q3. So the expectation, just apply the formula, and the variance, also just apply the formula. Again, the hardest part is just the algebra. And for n coupons, I just basically just generalize what we just did for general n. Hope you guys have a great day, and I will see you on Friday.